Good morning, everyone. Welcome to day 4 of the geometry workshop. Our first speaker for the day is Professor Mark D. Burke, and he is well known as a co-author of the textbook on computational geometry, which has become a standard reference in the field. He's a professor at TU Eindhoven, where he also chairs the algorithms group. Professor Mark completed his PhD at Utrecht University in 1992 under the supervision of Mark Overmars. His research is in algorithms and data structures, in particular spatial data structures. Today he will be talking about some recent work on constructing clique-based separators. And please join me in welcoming Professor Mark.
Okay, so good to see so many of you here in the early morning, or at least for me it's the early morning, but the advantage of giving a talk is that it's very unlikely that you fall asleep yourself. So also thanks for the organizers. As anybody who has ever spoken to me knows, I really love India, so I was very excited to get back here. Even more excited when I saw the wonderful program, so also thanks to all the other speakers for their very nice talks. Today I want to talk about some recent work I did over the past years on so-called clique-based separators. It's joint work with the people you see here. Maybe a special word about my former PhD student Chandor, who was really the person who started all this work. He's very great, and I worked on him on the first paper, and also one of the other ones. Also worked a lot with Leo, my other PhD student, who just finished on some of this work. And there's some more colleagues like Boris, Morteza, Daniel, and Tom, and Hans. But yeah, now let's talk about these clique-based separators. So what I want to do today is I first talk a little bit about planar separators. I hope that many of you are familiar, but maybe some are not. And also I'm going to give a geometric proof of the planar separator theorem, which ties in nicely with some of the things I will be showing later. Then I'm going to briefly mention two kind of trivial but still very nice results that you can get using normal separators, and then I'm going to move on to these clique-based separators and see what we can do with them, and especially how to construct them. So first, planar separators. I guess all of you know a planar graph is a graph that you can draw on the plane without crossing edges. And one of the nice things about planar graphs is that they have small separators. So what's a separator? It's a set of nodes such that if you remove the nodes, it falls into several pieces, let's say 2, and none of these pieces is bigger than some constant fraction of the original number of vertices. So let's say 2/3. Okay, and it's well known for a very long time that planar graphs have such separators of only size square root of n, and you cannot do better than square root of n. And Lipton and Tarjan were the first to show this. After that, there have been several other papers where they improved some of the constants or had weighted versions and so on. So let me give you this geometric proof of the planar separator theorem. Who has already seen this before? Okay, a number of people that I expected, but not everybody. That's good. It's a very nice and simple proof, actually. So the first thing you have to know is that every planar graph can be represented as the contact graph of a set of disks. Okay, so here you see that picture. So now we're going to work with this contact representation. And the idea is very simple. So here I have a contact graph, or a representation of my planar graph as a contact graph, and I'm simply going to find a square, and then that square is going to partition my disks into disks inside and outside, and disks intersecting the boundary, and the boundary disk will be the separator. Okay, so the question is, does a suitable square exist that partitions it in a balanced way and doesn't intersect too many of your disks? So what you do is you take the smallest disk, like this one, that contains, okay, this 36 is not really very important, but some fraction of the disk that's small enough, let's say n divided by 36. And now you're going to look at, this is the blue disk scaled by a factor 3, and I'm going to find my separator somewhere in between. Okay, so one of these red squares is going to be my separator, and I put square root of n of them at equal distance. Okay, so if I assume that maybe this is 1, then these distances are 1 divided by square root n. And I claim that one of these squares is a good separator. So let's see. So first of all, if you think about it, then it's kind of natural maybe that this should work, because, okay, big disks, okay, they're kind of dangerous because they're intersected by all these squares, but because of packing argument, you can have only very few of them, right? And small disks, okay, you can have many inside here, but of course, you're very likely to miss such a small disk. And so the computation is not very hard. You simply use the fact that if you look at all these disks, and let's forget about the really big ones, of which there's only a constant, then if you sum the areas of the disks, that will be a constant. The disks intersecting this, any of these things. And a disk intersects at most, well, if you look at the diameter, the distance between two of my squares is 1 over square root of n, so it will intersect at most this many disks, this many squares. And if you put these together, and then you will see that you intersect only square root of n disks. Oh, sorry, that's in total you have n times square root of n pairwise intersection, so one of the disks, one of the squares should intersect only square root of n of the disks. So then the second question is this actually a balanced separator, right? You should have not too much inside, not too much outside. And I claim that this is actually true for any of my squares. Why? Well, there cannot be too many things outside, because I have some fraction inside. That was the choice of my blue disk. There are n over 36 things inside. There also cannot be too many things outside. Why? Okay, and now I'm lying a little bit. If I partition this big square into 9 smaller squares, okay, since this was the smallest square containing n over 36 things, none of these others contains that many disks, so you're done. Okay, and again, I'm lying a little bit because there are things, intersecting two things, so you have to be a little bit more careful, but this is the idea. So this is a very nice proof. It has been observed by a number of people. Actually, instead of doing this square root of n things, you could also take a random square in between those things, and it works as well.
So Mark, I thought the Miller and had a different argument.
Wait,
it's a center. It's based on the center point argument. It's
but it's also a geometric proof.
yeah. That's no. It's their proof was some geometry, but
Okay, so now let's look at two very simple applications. So one is independent set. Okay, so in general, independent set in graphs is NP hard, also on planar graphs. For general graphs, you cannot do it in sub-exponential time, meaning that you cannot get a running time which is 2 to the power and then little o of n, if you believe the exponential time hypothesis. Okay, on planar graphs you can actually do it much faster than this, namely 2 to the square root of n. How? Well, with the separator it's kind of trivial. What you do is you compute this separator here. Okay, and then for each possible independent set of the separator, right, then I have, well, the square root of n nodes, so I have 2 to the square root of n subsets that might be independent sets. So for 2 to the square root of n things, I say, okay, let me guess that that is my separator, and then if I have picked some nodes here, then on this side, okay, if this was in my separator, then here I have to rule out this one, so I remove some nodes, I recurse here, same thing on the other side. Okay, and that's all. And you will get a running time which is 2 to the square root of n, that's the number of things we try, times, well, I recurse on a fraction of the nodes, and that solves to 2 to the square root of n. Okay, and this is actually, again, best possible if you assume the exponential time hypothesis. So this is a very, yeah?
So what is the fastest runtime to find a separator? No.
Linear time. Okay, here's another very simple application, distance oracles. So suppose I give you a graph, maybe edge-weighted, and you want to pre-process it so that you can quickly report the distance between two nodes in the graph. Okay, that's called the distance oracle. So this is a very basic result, and there's much better things known, but using these planar separators, what you would simply do is, again, take your separator, for any node compute the distance to each of the nodes in the separator, okay, and then recursively compute a distance oracle on this side and a distance oracle on that side. Okay, now how do you do the query? Well, suppose I want to go from here to here. This is my query. Well, that has to go through one of the nodes in my separator. So I simply check, oh, for this node, I have the distance from here to here. I also pre-compute it from here to here. I add it, and I do that for all the nodes on my separator, and I take the best one. Okay, very simple. If both of them are on the same side, it could be that you have to go via the separator, or maybe you stay in this part. So again, you take the best option, and that's it. Right, and that would give a structure with, well, depending on the size of the separator, but since our separator is size squared of n, I get n root n storage and root n query time. Okay, and by now this is actually far from being the best known. So in sort of a recent breakthrough, there was a paper that essentially had linear storage or nonlinear storage and logarithmic query time. Okay, so that was a brief introduction to separators. Now let's move on to these clique-based separators. And what we wanted to do is we wanted to do something similar first for disk graphs, right? We know that planar graphs are the same as graphs that you get from touching disks. So let's say, okay, if the disks intersect, maybe we can do something similar. But of course the answer is no, this is impossible, right? Because as we will see on the next slide, there could be a big clique, and if you have a big clique, there's no way you can get a good separator. So we started first looking at disk graphs, and then I'll also be talking a little bit about these other graphs. So here my disks are geodesic disks inside a polygon. Right? So I take a point, and then all points in the polygon at a certain distance, where I simply measure shortest path distance. I can look at map graphs. So map graphs are graphs that are the dual of a planar subdivision, but even if two regions only share a vertex, then you still connect them. Right? So that also means that you can have, like this vertex here, there are what, 1, 2, 3, 4, 5 things around it, so you get a K5 in there. And I don't know, you could also maybe look at string graphs. So as I mentioned, for disk graphs you cannot have a small separator. But what you can have is a small clique-based separator. So what's a clique-based separator? It's exactly the same as before. It's a separator that separates your graph in a balanced way. But now the size of the separator is measured in terms of the number of cliques in the separator. So normally you count the number of nodes, but now if I put a big clique in there, it counts as 1. Okay, so I have a separator consisting of a small number of cliques rather than a small number of nodes. Okay, and the question is, does it exist and is it useful? And the answer to both turns out to be yes. Besides looking at the size, which is simply the number of cliques, for some applications it's also important to look a little bit more closely at the size of the cliques. And then, here what you do is you take the logarithm of the size of the cliques and you sum that over all the cliques in the separator, and as we will see in a moment, that's also a relevant quantity. And of course, I don't want to, if I would just count instead of the log of the size of the size of the clique, I'm back to my normal separators and they don't exist in these graphs. So, question, do these intersection graphs have small separators, clique-based separators? And the first result that started all this was that if you have disk graphs or graphs of fat objects, and there's also a generalization to higher dimension, then there exists such a separator, and both the size and the weight are square root of n. So let's see. Proof essentially the same as before, and I guess you can see that now, okay, even, because the disk can overlap, okay, I cannot simply say, oh, the number of big disks, there can only be a constant because of a packing argument. But of course, once they start overlapping, you must create cliques. Right? So it's not too hard to show that by essentially similar computations as before, that if you do this, yeah?
Do you have the same requirement to the number of elements inside and outside, or one side and the other side of the clique?
That number of things inside and outside, that is the same as originally, so really based on the number of objects and not on the number of cliques, right? The number of cliques, that's what we count in the separator, but inside and outside, that's the whole number, all the objects. So you can do the same proof if you just want to show that the size is square root of n. Okay, that's not too hard. If you want to also argue that the weight is only square root of n, then you have to work a little bit more. And I'm not going to go into the details, but everything works out. And as I mentioned, this is not only for disks, but any kind of fat convex shapes where you can use some kind of packing arguments that should work. And it also generalizes to higher dimensions.
Just a quick question. So, does the results change significantly if you modify the definition of the weight function? So let's say polylog or any kind of constant function.
That's a good question. So we actually proved that the weight is square root of n for weight functions up to square root of the size of the clique, or actually size of the clique to the 1/2 minus epsilon. But yeah, that's a very good question.
So when you go in higher dimension, what are the dependents in the separator size?
So then this square root of n becomes n to the 1 minus 1 over d. Right, so n to the 2/3 in 3D, for instance.
Right.
And these things are all tight. If you just take essentially like a grid packing in d dimensions, then that's
Right.
that's what you would need.
But the constants would blow up, right?
The constant as a function of the
As you
dimension.
Grow up in dimensions.
If the dimension is not a constant, then yes, yeah. Okay, so before I want to talk more about these other types of geometric objects, geometric intersection graphs, let's see if they're actually useful. Right, so I want to revisit the previous two examples and see if it also works for these, and it's actually pretty easy to see that indeed it works. And you'll also see for the first one, this independent set thing, that the weight is important. So independent set, well, you just do exactly the same algorithm. Right? I don't change anything except that I take this clique-based separator. Okay, and now the argument used to be that, okay, you have only square root of n nodes in your separator, so the number of subsets you have to try is 2 to the square root of n. Now I can have a linear number of nodes in it, but in each clique I can take at most one thing. So that's why everything works. So here, okay, I have my separator, maybe consisting of 2 cliques. So what I have to try is I have to try well, independent sets, maybe one node from here and one node from here. Right? Or 0 from there and 1 from there, and so on. So if you now do the computations, it's pretty easy. What's the number of subsets we have to try? Well, at most one node for each clique. So it's the product of size of the clique plus 1, right? Yeah?
It depends which node you take from the clique.
Yeah, so I have to try all of them.
Okay.
Right, so that's why here, for each clique, I have number of nodes in the clique plus 1 number of choices.
Okay.
Right, I can try all the nodes, or I simply don't take any of them.
Okay.
Right, and I have to take the product of this over all the cliques. Okay, and then the product of this, I can write this as 2 to the, and now I take the sum of the logarithms.
So why the log is?
Because this is,
Take it to power to make the
right.
product with some.
yeah,
Oh, this is the weight.
yeah, and okay, so this is just basic algebra, and now here I see, oh, this is my weight function, and so now I know that the weight was square root of n, and not, if you have square root of n cliques, okay, obviously the weight cannot be more than square root of n times log n, right, because each clique has its most size n, and then you would get 2 to the square root of n log n, but here for these sub-exponential algorithms, the goal is also to try to get rid of these logs. So here it nicely sums to 2 to the square root of n, which is optimal. So that's nice, this works very nicely. Distance oracles, also exactly the same, except that you get an additive error of 1. Right? Because if what I do is I compute for each node the distance to each of the cliques, not the distance to each node in each clique, but the distance to each clique. And then if I want to go from here to here, okay, I try, do I have to go through this clique or this clique? if I take this one for instance, okay, I know the distance from here to the clique, I know the distance from here to the clique, but I don't know if I end up in the same node or not, and in the second case I need one extra link. Okay, so that's why you get an additive error of 1. And this...
This recursion, right? So the plus 1 should show up at... plus 1 should add up to 50.
No, because if I recurse, then on what do I recurse? On a path that, say from here to here, that only stays on this side. So the recursion, so the bound is either you go via a clique, then everything has been pre-computed, there's no recursion, or you have a solution that stays on one side, and then, okay, since you don't, yeah. So, yeah, so this is, again, very similar, and somehow surprisingly, this was a new result, even for, unit disk graphs, for instance. There were only distance oracles with a multiplicative error that were using less than quadratic space and had less than linear query time. So this is quite nice and powerful, and I hope and expect that, okay, if you now follow the whole sequence of things that have been done on planar graphs to improve things, maybe some of these things could work here as well. But we didn't look at that so far.
So Mark, so you're talking about the hop distance.
Yes, yeah.
But
okay, so this only works for hop distance. Very good point. Yeah, so this statement is also true for hop distance, but you're right, for the original thing, that worked also if you have weights on the edges. Here it's only hop distance. Okay, there's a whole bunch of things you can do, and I should probably mention more work by other people that, okay, so I'm bad at many things. One of them is that I don't read enough. So there's lots of results out there that I should read, but that I didn't read. But yeah, so if you have a clique-based separator, you can immediately do independent sets in running time 2 to the weight of the separator. You can immediately do feedback vertex sets, same running time. You can immediately do coloring, and here it's 2 to the size instead of 2 to the weight. You immediately get this distance oracle. Yeah, here you need to do a bit more, but we also showed that if the objects are more or less the same size, then you can do dominating set or Steiner tree. You have these, this is actually also I think very nice. If you take a disk graph, but now it's directed in this following sense. So if the center of one disk is inside another disk, then I put a directed edge. So this is called the transmission graph. And now even the question, can I actually go from one node to another one? You know, forget about the distance, but can I go from here to here? That's already difficult to do with small storage and fast query time. Right? For undirected, okay, you just compute connected components and you check, oh, is this in connected component 5 and this as well? But for the directed setting, that doesn't work. And also here, based on these clique-based separators, you get the best known result so far. There was a recent paper at Sausage, very nice, where, okay, they they also use clique-based separators. Based on that, they have some clique-based clusterings, and they do something about computing almost exactly the diameter in unit disk graphs, which is also a very interesting and difficult problem. So here you see an overview of the results that we have so far. I talked about clique-based separators in disk graphs, right, where both the size and the weight are squared of n. This is optimal. Fat convex objects. I will now talk a little bit about these results, if I have time. Map graphs, pseudo disks, and actually polygonal pseudodiscs and geodesic disks in arbitrary metrics. And for each of them, I'm going to sort of hand wave or sketch, if you will, the main idea in the proof. And there's also some results on higher dimensions. Okay, so let's see, how do we construct these clique-based separators? Well, we already saw that if the objects are fat, let's say disks, then essentially we can have the old proof. Okay, and this uses several things. So the objects need to be fat, because basically there's some kind of packing argument, or saying, oh, if I have too many of these objects, then they must start intersecting, and therefore I have large cliques. You also need bounded doubling dimension of the underlying space, because to argue that this was balanced, I was saying, oh, take this small square, blow it up by a factor 3, now partition into 9 pieces of the same size as this, and then each of these pieces contains only a few things. But that requires that this bigger red thing, that I can decompose it into constantly many copies of this one. Right, and that's, that requires bounded doubling dimension. So that means that, for instance, if I want to do geodesic disks inside a simple polygon, okay, a simple polygon does not have bounded doubling dimension, if you look at that space, so things break down. Okay, so I want to show you 3 different proofs, because they use 3 different mechanisms which are maybe nice to see. So first, map graphs. So a map graph is, you could define it as, you take a planar subdivision, you take the dual graph, but you also connect things if they only share a vertex. Or I could say it's the intersection graph of things that are touching, right, the regions, where, whenever they touch, even in a single point, I connect them. So here there's sort of these empty regions that don't count, but I have these other things that form my nodes. So what I do is I can take, the easy thing is I would say, okay, take my objects, okay, the faces of my map graph, so those are the blue nodes. And now I pick a set of red nodes that are sort of witnesses for the intersections. Right, so for instance, these 2 regions are intersecting, or they're touching. Actually, they have an edge on the boundary. And there's a red node here that is sort of a witness that it's because it's on the shared boundary between them. And actually here I have 2 witnesses for this one, also on this side. And you see that here, this red node, so there are many things around it, so I get a big clique, but there's a single thing that is a witness for this whole clique. Right? That's the point that is shared by all of them. So what I could simply do is, it's not...
So why is there a red node on the edge next to the vertex that you just showed? So sometimes there's a, yes, so sometimes it's on the edge.
Okay, I would not need it, but in the construction, I mean, you have, okay, so what we will do is we will prove that this graph has linear size. Okay, so we have a certain way of generating these witnesses, and it just generates some witnesses that are not really necessary.
Some other edges don't have it, so that's why I'm asking.
Yeah, I don't know. Could be because at some point you get tired of putting things. Yeah, so I guess it's kind of clear that if you have a map, you can do it with a linear number of things, right? If it's, you simply put something at every vertex, at every edge, so that's one. And that is linear size. So what you could simply do now is you take this new graph, compute this, that's planar, compute the separator, And then for each, okay, there may be some blue nodes in the separator, fine, you put the object into the separator, the face. If it's a red node, okay, there's a whole clique around it, you put the whole clique. Okay, but that would give a weight. Okay, so the size would be square root of n, because this is a planar graph of linear size, we apply the normal separator theorem. But the weight would be square root of n times log n, because we don't really have a control over, you know, these red vertices of high degree. They're expensive, right? They are large cliques, but we don't have any control over how many of them we put. So there's a nice trick, and that's, I'm going to replace these red nodes by little gadgets like this. So take one such red node, okay, that's maybe this one. These were all the blue nodes adjacent to it. And I put like a tree structure. So you can also look at it as here, where, okay, you have this tree, but also you put these rings in the tree. So here I have this tree, but I also have edges connecting things at the same level, and maybe I even triangulate between the levels. And the idea is that now, if I now apply my planar separator theorem, okay, so this gadget, it does not blow up the size too much, right? Because the size of the gadget was the original degree of this inner node. So the size is fine. And now, essentially, if my separator sort of, I don't know, did something like this, okay, then it's maybe, you know, separating this part of the clique from that part of the clique, but kind of. But then here, that would correspond to, okay, you have to go up pretty high in this tree, and then I put, for each node, I put all the descendants in my separator, and that means that, okay, if I go up to a certain level, height h, I can put only 2 to the h nodes in my separator, so my weight is nicely logarithmic in what I want. So this is the basic idea here, which I think is a nice trick to get the weight down to square root of n. And that also meant that some of these sub-exponential algorithms, the previously best running time was 2 to the square root of n log n, and now we get 2 to the square root of n. So that's nice. Pseudo disks. So this is a very nice open problem for you to work on. We have, okay, in general, the bound that we can get on the size is n to the 2/3, okay, and the weight is n to the 2/3 log n. If they are polygonal, and n would now be the total number of vertices, or let's say nv is the number of vertices, then we can get this square root of total number of vertices. And I don't know what the right answer should be. Is it in general for pseudo disk, should it be n to the 2/3 or should it be square root of n? And the way we prove it is we take a point, a set of points that stabs all the pairwise intersections. So it's a little bit like we did before with this witness set. Okay, and now if you look at the hypergraph defined by, okay, where the nodes are these red points, and each region defines a hyperedge, right? So I have a hyperedge like this, and for this thing I have a hyperedge like this, and here it's this one. So we want to pick these points in such a way that there is a planar graph on the red points that is what is called a planar support, which means that for every hyperedge, like okay, look at this region, the hyperedge are these three nodes. If I take out these three nodes, then the induced graph is connected. Okay, if you can do that, that's called a planar support. And now what we show is that if you take a normal separator on this planar support, then you actually get that translates into a good clique-based separator. Yeah. And then if they're polygonal, then you can get the planar support because of small size, linear size, because every two polygonal pseudodiscs, if they intersect, one will have a vertex inside the other one. So the vertices simply serve as this red set. If they're not polygonal, then okay, you have to do something else. Okay, so unfortunately, I don't have time, it seems, to talk about the last thing we did, which I also find very nice actually. That was in Solstice this year. So this is about.
We have 7 minutes. We start endlessly.
Okay, great. So I will now tell you about this latest result, which is very nice. So it's about geodesic disks, right? So you take a point in a metric space and you look at all the points within a certain distance. And this is very general. You can sort of take any kind of metric space in 2D. So you can take a polygonal domain and look at geodesic distances. You can have a terrain and look at the shortest path on the terrain. You can have weighted regions and look at shortest path in these weighted regions. Note that they're even here already shortest paths are not unique and so on, but that doesn't matter. We can still show that you have a small clique-based separator. And one of the tools that we will be using is that for a string graph, and a string graph is sort of a superset of all other intersection graphs. Every intersection graph of connected objects is also a string graph. There you can have a normal separator whose size is square root of the number of edges. Okay, number of edges can be n squared. So first of all, it doesn't help you much, but we will use it because what we will do is we will get to a situation where the number of edges is small. And how do we do that? Okay, so first we make sure that the ply is small. So the ply is, for every point in the plane you count in how many objects is it contained. That's the ply of that point. And then the ply of the whole thing is simply the maximum over all possible points. And I simply say, whenever I have a point that is stabbed by, right, so here the ply is 4. Whenever I have a point that is stabbed by at least n to the 1/5 objects, I take them out and I put it as a clique in my separator. Right, I can do that only n to the 4/5 number of times, obviously. Okay, so this one is removed, maybe here I have another clique and I also remove it. And now I'm left with a situation where my ply is n to the 1/5. Okay, so how do I use that? Now I want to prove that if I now look at my intersection graph, that the number of edges is smaller, cannot be n squared. Okay, and then once I'm here, now I can apply that result on string graphs and say, there's a separator whose size is square root of number of edges, so also n to the 4/5. Okay, so my final separator is this separator from the string graph plus the cliques that I removed in step 1. Okay, so intuitively, how do you prove that the number of edges must be small? So let me define x to be the number of crossings between the edges. If I embed every edge, so this is an edge because this object intersects with this one, I embed it as the shortest path between them. Okay, if I have multiple options, I simply pick one. And now I look at the crossings. And first of all, because of the crossing lemma, I know that the number of crossings is at least number of edges cubed divided by n squared. Or in other words, this puts an upper bound on the number of edges in terms of the number of crossings. So then I'm going to show that the total ply is at least the number of crossings times this. And that's a crucial step. And then, okay, if this is the case, then of course, well, there must be one of these crossings whose ply is more than n to the 1/5. Well, that's a contradiction because the ply was small. So the crucial step is really to show that if you have many crossings, then the total ply must be large. And there's a very nice and simple, well, very nice argument. So if you look at a crossing, okay, so this is an edge from this object to this one, I have another edge from this one to this one, and they cross. Now look at these two sub-edges, and suppose that this one is shorter than that one. And this point is a point that is in the common intersection of these two things. This here is sort of the midpoint, meaning in the common intersection of these two things. So this is completely contained in this object, and this is completely contained in that object. But then, if this is shorter than this, then all these points must be contained in this, in this object, right? Because this plus this is longer than this plus this. This stayed inside my object, and this was a geodesic disk, so this distance is smaller than this one. So all these points here must be in this green object. So if I have a crossing, then it contributes ply to all these crossings here. And now, okay, you have to do some more work, but that implies that if you have many crossings, many of these crossings contribute to the ply of many other crossings. So in total, I get a very large ply. So that's the basic idea.
So this depends really crucially on the fact that it's the geodesic disk and the metric and
exactly
everything there being a longest and everything shorter than that.
Exactly. So this is the point where we use that we're working with geodesic disks. Yeah. Yeah. And then we do the same thing, and then using some more complicated machinery, sort of recursively doing things, we can actually improve the result. So this is, I guess, my final slide. So this is an overview of all the sizes, and if you want open problems, then for none of these we know whether they're tight. I guess this is tight, but that's it. Yeah, and there's all these applications that I think one can work on as well that are very interesting. And that is it for now, so thanks a lot.
Thanks, Professor Mark. We can take questions now.
I'm not entirely sure if this is in any way useful, but what if you force all the vertices that you pick for your cliques to have the same neighborhood? So essentially that way, for the independent set at least, you only need to pick one per clique.
Yes, so I don't know how to do that. It would be in some applications quite useful. So for independent set, for instance, it doesn't really matter too much, but if you want to do dominating sets, then something like that would be quite helpful. But I don't think that this is actually feasible to get that.
Thanks.
Any other question?
Yeah, earlier I had been wondering about anisotropic distances rather than symmetric distances, and I think maybe that's going to break down because of the way that you use distances in your argument, but I'm not sure.
Yeah, I think that is not going to work. Yeah.
And when you talked about terrains, I immediately thought about it's harder to go uphill than downhill, and so the distances are different.
Yeah. But yeah, I don't think that that will work. But that would be also an interesting problem.
So let's thank Professor once again.
who is a faculty at the University of Augsburg in Germany. He completed his PhD at ETH Zurich and subsequently held postdoc positions at KTH and KTH Royal Institute and Saarland University. He works on approximation algorithms and also online algorithms. His work on approximating graphic TSP by matchings received the Best Paper Award in Fox 2011. In this talk, he will discuss his recent work on Euclidean TSP, a linear time approximation scheme that is optimal under the gap ETH conjecture. So please join me in welcoming Professor Tobias.
Yeah, thank you for the nice introduction. Yes, I'm talking about a linear time gap ETH tight approximation scheme for TSP in the Euclidean plane. And this is joint work with Hang Zhou, and it's really amazing to work with her. So if you have the chance to work with Hang, that's really great thing to do. So most of you know Euclidean TSP, but to be complete, I introduce it again. We have points in the plane, and I'm only talking about the Euclidean plane here, not about d dimensions. The distances are the Euclidean distances, and the goal is to connect all of those points with a cycle, minimizing the overall weight. I think I don't have to say much more about that. What are the known results? So, before the first result, like in 1998, it was actually a major open problem whether you could actually even do a 1 plus epsilon approximation in polynomial time. And then at the same time, Joe Mitchell and Sanjeev Arora came up with an approach to get actually a polynomial time approximation scheme. They also won the Goethe Prize for that result. And basically the problem was solved then, right? But I mean, of course you can do more. Because the running time was polynomial, but there are two dependencies. There is a dependency on n, and there is a dependency on epsilon. Because we have an approximation scheme, so we actually have an infinite number of algorithms. Like for each epsilon, there is a polynomial time algorithm, where this specific epsilon is a constant, right? So therefore, it makes sense to optimize in both epsilon and n. And that was caught up immediately, basically. Like Rao and Smith had an approach based on missing the word right now. They got 1 over epsilon to the 1 over epsilon n log n, so they improved the running time a lot. So this was like an important work that also had influence afterwards. Then in 2013, Barthal and Gottlieb got the first linear time algorithm. So that means the running time is rather bad with respect to epsilon, but they made a big leap forward by actually having only n here in the running time instead of n log n. So this is optimal in n, but it's not optimal in epsilon. And then, with some really nice ideas, Gisvalou-Debug, Nederlof, and Bekdrisky, I hope that I pronounced it right, obtained another algorithm that is tied to the dependence of epsilon. That is like tied. What does it mean tied? I mean, it's of course based on assumptions, and the assumption is a gap exponential time hypothesis. So subject to the gap ETH, the dependence on epsilon of this result is tied, but the running time is n log n. And our result is to bring the Barthal-Gottlieb and the Gisvalou-Debug et al. Together, and we get a 1 plus epsilon approximation algorithm. Our dependence on epsilon is like optimal, and the dependence on n is also optimal. So that is, yes, clearly like better than n. You would not be even able to read the input if you want to be better than n. And those guys showed that such an algorithm would break the gap exponential time hypothesis. Yes?
So previous result also had the real RAM model with atomic floor operation assumption or something else?
Yes, that's my next slide. But that is a very good point, because like linear time just doesn't work if you don't consider the computational model. Because if you like take an arbitrary model, you could as well take sort of some comparison-based algorithms, and then even sorting requires n log n. So like with any model, you cannot have linear time. So Barthal and Gottlieb used real RAM with atomic floor function, and we use the same model. So like they were specific about atomic floor or mod, so would be the same for us actually. So we only stated it with atomic floor because I don't think it makes a real difference. And the open problem stated by Rao Smith actually also assumed the real RAM with atomic floor function. Yes?
What is atomic floor function?
Yes.
That means that I basically can round numbers in like one step.
Like
So
down or?
Like I can round like a fractional number to integer
So then
in one step.
Okay.
In an atomic manner.
So one step means you cannot do it, apply again, or what?
No, I can apply it as often as I want,
Yeah.
but like one step of running time means one rounding operation.
So what is atomic? What is atomic? It's just a floor function.
It's just a floor function. It's just an atomic in like it's one step within the machine.
Ah, okay.
That's
Okay. Unit
maybe a
cost.
too complicated word for a very
Okay.
simple concept.
Okay. It's just with the floor function. It's
Yeah.
just okay with the floor function.
Yeah. Yes. Yes, Barthal and Gottlieb has the same model as the n log n algorithm does not. No. The n log n algorithm does not have that. They don't need it because, like, if you have this extra log n, then you can do many more things. And like, for instance, the floor function would be easy to do anyway if you have an extra factor log n. So I mean, it's pretty clear that without like assumptions on the machine model, you have no chance to cut off this log n. I will actually like go into a bit more into detail of what the difference is, because most of the previous results actually would run in linear time if you assume this model, but the entire result still requires n log n if you assume this model. It's not simply a choice of model and it's getting better. Also, the previous result needs serious improvements, like the ones that we do actually, in order to get down to linear time. Then some remarks to that. This floor function does not have to be applied to very big numbers. Like if we apply it to numbers in the with log n bits or of log n bits, then it's sufficient to only apply the floor function to those types of numbers. And the real number operations make things convenient, because then we don't have to like deal with like little rounding errors. But in the end of the day, if we have a little error, that would not make a big difference. So that we have real number operations is not really essential. Why do we still need the real RAM? We need the square root function. So the real RAM has a square root function as like a constant time operation. And in the Euclidean plane, we cannot even like efficiently get the distance between 2 points without the square root. And due to like, since those two parts are not really necessary for us, we can really actually claim gap ETH hardness, because the gap ETH is actually, I think, in the word RAM model, and we would lose running time in n, but in epsilon we are still right. So the gap ETH hardness still applies. So we are still gap ETH tight with our result, and yeah, in this model that we are working, we have like this optimal running time. Yes?
When you say it's a gap ETH type, do you talk about dependencies in epsilon, nothing in the polynomial?
Yes, gap ETH talks about dependence on epsilon. So gap ETH says nothing about n. And yes?
Sorry, very basic question. If I have 2 points on the plane and I don't have the real RAM model, is the best way to approximate distance just to Taylor expansion?
I mean, one way or the other, you have to somehow compute the Euclidean distance, right? I mean, I don't know how efficient the Taylor expansion is, but I mean, you would need somehow more than a constant number of operations, right? I mean, it's like not super many operations that you would need, but if you really want to have linear time, then you don't get away. So for this talk, I have to actually review quite a few old results, because otherwise it's hard to explain what the new part is. So our algorithm is building on Aurora's quadtree descent. That means, what's the general idea? We have a bounding box, an L by L bounding box that is small enough so that we can deal with things efficiently, but big enough so we don't lose too much error. So like some O of n over epsilon is enough, such that we now can like scale the whole instance to an L by L square, and then we can move those points to integer coordinates, and we don't lose too much by that, and we are in a good shape. Then we do a shifted quadtree, that is, we like where the crossing points of those, like we shift the whole squares by some like A1 and A2, like horizontally and vertically, in order to actually deal well with which types of cuts are with the quadtree. So like the quadtree is, we have the square, and then we have those subsquares and subsquares of subsquares and so on. And then we introduce portals, and due to the portals we can have like sub-solutions that collects the points inside of a square and connects the tour to some portals here. And then we can set together those squares in order to get a solution for the bigger square and so on. So that's like well known. Then an important step that, yes?
Could you like explain what portals are?
What portals are? Oh, okay. Portals are basically, think of Steiner points. That is, like on those boundaries here, we introduce some additional points where the tour goes, and the reason is to have like a small interface between those squares. Because what you want to have is, you want to have like a small number of separate solutions that fit well together, and if you don't have the portals, things would not really fit together. So you lose something by going to the portals, but what you win is that you have fewer configurations that you have to deal with.
So you choose random portrait, is it shifted or what? So you said choose random. What is the? How do you choose random? Is it a shifted?
I choose two numbers, A1 and A2, uniformly at random.
Oh, it's like shifted.
And then like we have different levels of lines. Like we have like this outer square, and then we have this subdivision here, and then we have smaller subdivisions. And in the end, the number of portals depends on the level in which we are. Because the idea is to build the solution from the smaller squares to the biggest squares. So like we compute solutions for all the small squares and set them together to bigger squares. And therefore the number of, so the portals in the small squares are much closer together than in the bigger squares. And then actually on the next slide we can see this well. What can happen is that we have such a line that has lots of different crossings like this here. And then it makes a difference of like, are we, like how much do we have to pay to go to a crossing? And if we randomize things, like if the probability to have, what we want to achieve in the end is the probability to go a long way should be small. And like half of the distances are, like half of the distances we have to pay are in the smallest squares, so that is the smallest possible distance. And then a quarter is in the bigger ones and so on. So that's why we need in the end the random shift in order to like mitigate this type of detours. Like we don't want, like otherwise it's very easy to create a worst case instance where things don't work anymore. And like this random shift is also a key property for Aurora's patching lemma, because it still can happen that we have some like line like this is of this quadtree, of this boundary. We still can have such a line that is like crossed many times. And due to the random shift, we can actually show that this happens with a relatively small probability. And what we want to achieve is that overall we have only a small number of crossings. Like we have a certain number of portals and everything, but even so, the portals might be like more, it might be many portals. We do not want to have more than a constant number of crossings between like two cells. And that we can actually do. We can like pay something extra in order to reduce the number of crossings. So like here we have introduced those dotted lines, and together with the dotted lines we can now run a tour like this here, and then we have only one crossing here instead of many crossings here. So this plays a key role in the next result that I'm talking about. But I mean, this is like sort of a key idea. It is necessary for Aurora's result for d dimensions. For 2 dimensions, it actually makes things more efficient. So now, Kisvaludi-Buck et al. Had genius idea. That is, they had some sparse, sparsity sensitive patching. So it's the same patching that I explained to you before, but instead of saying, okay, the number of portals depends only on the level in which we are in the quad tree, it depends on the number of crossings that we have. In a somewhat counterintuitive way, like if we have few crossings, then we want to have many portals, and if we have many portals, many crossings, we want to have few portals. Why is that? If we have many crossings already, then we are in a situation that is rather unlikely, and we can actually afford to like accumulate some potentials in order to pay for that. And then we can get away with like accumulating potentials in order to get away with few portals. And then we need relatively many portals if there are few crossings, because those crossings somewhat do not interact with each other well. So we cannot afford to take a long detour for those portals. And then the exact dependence is like this function here. Like k is the number of crossings of a side of some square, and then we have something like 1 over epsilon square k. If k is like 1 over epsilon, we have 1 over epsilon crossings, and so this turned out to work really well, actually, because they introduced some notion of like proximity. The rough idea of this proximity is that what's the distance of different portal crossings. So what's the idea? It's like if the portal crossings are very close together, like if they're like points that are close together, and want to cross, then we can like combine them pretty well to one crossing. And if they're far away, then they build up some potential, and then we can actually afford to do other things. And this is like represented in this function here. So this is a function that tells us like how much do we actually pay for those crossings. So it's a bit technical, but so then the next result that we will also need for our work is like we will also reuse Bartal and Gottlieb. Bartal and Gottlieb had like a much stronger result than what I stated here, but Bartal and Gottlieb applied with epsilon equals to 1. This is what we need for our result. So epsilon is this error. So if a 1 plus epsilon approximation, we are actually only interested in a 2 approximation here. To get a 2 approximation, we can apply Bartal and Gottlieb, and the whole thing runs in linear time. So there's no epsilon left. Everything is a constant. So we simply get linear time algorithm, and that we can apply. Now, before we can state the algorithm, like we need some more definitions. You have to bear with this for a little bit, then it becomes more clear. So we have the concept of active crossings. Active crossing is we have our square, and there could be 2 different types of crossing into the square. It could be like the tour goes into the square, collects some vertices and goes out, or it could be that a tour goes into the square and directly goes out somewhere else. And an active crossing is a crossing that also collects something inside the square. That is needed here. So like a not active crossing is a crossing that like jumps right through the square and goes out. So in the not active crossings we deal with separately. So like this is like another part of the thing that's also where our dynamic program in the end changes, that the non-active crossings we deal with separately and directly, in order to not have to deal with like lots of different squares. So, and then we have like Z of something is like the set of portals, like similar to Kisvalou-Debug et al. The portals are like not simply depending on the level of the quad tree, but also on the number of crossings, and we have also additional crossings due to some extra things that we compute. So based on those parameters, we have the definition of our basic solutions, and our basic solution now is a solution that for every side of a square in the quadtree dissection has that the active crossings are so these are the active crossings at this side, at this like facet of the square, are within the set of like portals that we have determined for that facet, and like the multiplicity of each active crossing is at most 2, meaning that no portal is used by more than like a single portal could be like used twice by the tour, but not more than 2 times. So now I think done. I've tortured you enough with the technicalities. Now we come to the algorithm. So the algorithm is, the first thing we do is we compute a tour approximation T using Bartal and Gottlieb in linear time. Then, well, the second thing is we pick a random shift A, so this is vector A, and compute a compressed quadtree. So I have not talked about compressed quadtrees, but the thing is, if you compute a quadtree, then actually the number of squares that you get is more than linear. So you can only deal with a linear number of squares, and you can achieve this. This was also done by the previous works. Basically, you can stop, like if only one point is in the square, you don't have to subdivide it more. So, and also like squares in which nothing happens, you don't have to do anything. So like from one square with a point to the next square with 2 points, like if there are squares in between, you can skip them basically, and then you can see that you are left with only linearly many squares, and then it's well known that you can do this in linear time. And there's some paper of Chan that, like, it's actually non-trivial. It's also, this requires this machine model, because you have to compute some type of shuffle product in order to actually get this this compressed quadtree, but that's then doable in linear time. And then what we are doing is we use our solution T, our approximate solution T, in order to add additional portals. That is, if we have some cell in the quadtree that is entered by our tour T, by our approximate tour T, then we choose like one of, like, there could be many crossings of some phase like used by our tour T, but we only save one of those. So that is, we add one additional portal for each phase if this phase is used by our tour. Like, for simplicity, everything like conceptually still would work if you simply think of, like, we have our tour approximation, and then all those crossings are additional portals, but we don't need all of them, and we cannot afford all of them because otherwise we lose linear time. One of them is enough. And then when we have done that, we use a dynamic program computing an optimal R-basic solution. I mean, we have to be careful with a few things within this dynamic program. It's slightly different from the approach of Aurora, but it's like there are no major differences. So the main thing now is that like the R basic solution is good enough. So the R basic solution using our computed set of portals, that this is a 1 plus epsilon approximation. This is needed because all those steps now are linear time. That is, all we have to do is to show that the solution that we computed with this algorithm is good enough. That is, we want to construct an R-basic solution of prime from an optimal solution opt, such that the total cost is at most 1 over R. So think of R 1 over epsilon, so think of this as epsilon, think of R-basic as 1 over epsilon basic. So that means from now on we only have to show an existential proof. We do not have to talk about running times anymore. So everything we do from now on is simply to show that the solution is good. And now we have a construction that is, therefore we now assume that we know the optimal solution opt, the optimal solution, and that we have our true approximation T available. Now S is the optimal solution together with a tree. That is, we take not only the optimal solution, like previous approaches would only take the optimal solution, and we have like two tours together, opt and T. That's our graph S. And then one of the ideas that we have is that in order to charge, we cannot, it's not necessary to only charge with respect to opt, but we can also charge with respect to S. I think I come to that later. I don't want to go ahead too much now. Yes, then we use the concepts of Kisfaluli-Bak et al. They have a concept of near crossings and far crossings. Like NS are crossings, like if the proximity of portals is very close, then this crossing is like in the set NS. And if the distance is rather far but not too far, like if it is like within the same side of the square, but far away, then it's GS. And then we have like line segments PF that connect vertices from NS to successors. So what is that? So that is, we have our side of the square, and then we have like PF stands for patching forest. So this we chose this name to be consistent with Kisfaluli-Bak to not increase confusion. So we have a side of a square, and then we can like separate it into like segments where certain numbers of crossings happen. So that's why we can like a single face can be like separated into separate like crossing segments. These are these PF. And if they're close together, things are somewhat easy to deal with. We can like connect a crossing to a neighboring crossing if they're close together. So they basically act as one crossing, but we can use the joint potential of those two. Then step 4 is like this is a set of line segments, and eta is now one line segment among those. And this now contains an active crossing. And now we look at X. And this X can only have like one crossing from these far away types of crossings. So X is the only point in the segment that belongs to this, these G types of crossings. And then we connect that one to the closest portal. And then we apply the patching lemma of Aurora, basically the patching lemma of Aurora to get our solution. Then in order to show that the solution is good enough, point 1, 2, and 5 are basically clear from previous results. Then what's left is 3 and 4. Like for 3 and 4, we have to work a bit harder to show that we only lose an epsilon factor from those. And for step 3, we can simply apply lemma 5 of Kaffik-Hispalu-Debug et al. Because they dealt with that already. They like if we have near crossings, then step 3 like was about near crossing, then we can deal with that. And crossings like if GS is greater or equal to, they can deal with like crossings of step 4. And that's actually that is the whole point. I mean, this needed all this introduction to bring you to the point that they can only deal with this GS greater or equal to, and they also have an example that it really does not work with a single crossing. That is, if this, so if you have like a square, and the side of the square, and there's really only one crossing going in, then they have a problem. So if there are two crossings going in and they're close together, then they can like bring them together, but they still have a problem. If they have a square and there are two crossings going in somewhere, then they can deal with that. And our contribution is we can also deal with the single crossings. So what Hispalu-Debug et al. Did before is they used Rao-Smith in order to deal with the single crossing cases. And with the single crossing cases, at least the dependence on epsilon was very good. But the n log n came in from this GS equals 1 case. And yes, now we have this lemma here. So what's left to show is if there is only one crossing, like think of there is like a site which has only a single crossing, then we are good. So we see if F is T crossing. I think the slide is not entirely correct. I mean, this is a correct statement, but that's not the only thing left to show. This is actually like one of the new results that is rather easy to show. That is, what this result is about is if the optimal tour has a crossing somewhere and there is a T crossing, like T was our approximate solution. There it helps, so like if the T crossing and the op crossing are very close together, then we can move the op crossing to the T crossing and we have introduced a portal for the T crossing. So that's why we actually do not pay much for that crossing, and therefore we are good. If we have an op crossing and a T crossing that are far away from each other, then this behaves like two crossings, and then we can apply Hispalu-Debug et al. And we get our result. So what's stated in lemma 6 here is actually an easy case that we have to show. So what's left to show then afterwards is like if it's not a T crossing. Yes?
One more minute.
1 more minute. Okay. Then I'm trying to, let's see how to do this best. We have like the definition of interesting crossings. So we have one crossing, it's not a T crossing, we want to show that we are good. We have now several things. So the thing is, like the single crossing, we can charge against things. We can charge the single crossing against the length of an edge. And if it's very long, then we can just take the length of this edge E in order to pay for a detour, and then we are good. But if it's very short, then we are in a difficult case. Now, how do we deal with difficult cases? So that's badly cut if it's such a difficult case. And then we can have the case that, like we have this difficult case, and the red one is our approximate tour. The green one is optimal tour. If like both of those guys go out to the top, they can be far apart, which is good because then we have like the two crossing case, or they can be close together. If they're close together, then we can use that here is a portal in the middle, and this helps us to like show that we actually can like use this red tour for paying for the detour cost. And finally, we have the situation that it does not go to the top but to other places, and then the idea is to use this this approximate tour to pay for the portal crossing here of this edge, which can happen in different ways. And the idea is to take like a shortcut of those points and then to pay with a difference. That is, we have like from the smaller to the bigger squares we have done these things, and then eventually we add up at the square that we are dealing with, and in that square we directly connect the two endpoints of our approximate tour. And the other tour, like originally the tour had to enter like this region here, and this shortcut gives us a certain charge, and this charge we can use for paying for the detour of this badly cut edge. So that actually finishes my talk. So we have shown gap ETH type 1 plus epsilon approximation for TSP on the Euclidean plane in linear time. And the open problem is to generalize it to d dimensions. So thank you for your attention.
Thanks, Professor Toplis. Any questions?
The stained tree, is there any equivalent stained tree running time? Do you have any indication of this?
I have not thought about that. I could imagine that things also work, because like at least Aurora scheme worked very smoothly also for many other problems, but honestly I just have not thought about that at all.
So,
yes?
So there are many details, but one of the critical reasons that it doesn't generalize to d-dimension is sparsity patching lemma.
So actually for a long time we thought that it does generalize, and most things do, but I remember this was a critical case where we the thing is like if you charged against like two crossings, these two crossings have to sit on the same line. And that's not the case anymore for d dimensions. And we found then some examples that our analysis actually did not work. So we actually believe that it can be done for d dimensions, but the ideas that we had just didn't go through. Yeah.
So use the real-time with a flow function. Was that computational model also used in the previous papers?
Yes.
on this problem, all of them?
Yes, so this model was used in Bartal Gottlieb, and this was an open problem stated in Rara Smith. Like the other papers didn't need it because they did not have linear running time.
And what is best known for D-dimension?
Okay, let's take more questions for the coffee break.
Excuse me, for D-dimensions?
What is the best known result
What is that?
for D-dimension?
What's so Kisvaludi?
No, what is best known? That's what I am.
No, Kisvaludi Bak et al. Show it for D dimensions, so that's the best result now. And Bartal Gottlieb is also for D dimensions.
Okay, we can take other questions during the coffee break. Let's thank Welcome back, everyone. For our next session, we have Professor Saket Saurabh as our speaker. He is a professor at the Institute of Mathematical Sciences, Chennai, and an adjunct faculty at the University of Bergen in Norway. He did his PhD at IISc, followed by postdoc at the University of Bergen. A leading researcher in parameterized complexity and graph algorithms, Professor Saket is a recipient of the prestigious Shanti Swarup Bhatnagar Prize for Science and Technology in Mathematical Sciences. Today he will talk about his recent results on point separation and obstacle removal problems. So please join me in welcoming Professor Saket.
Thanks, Rachna, for your introduction. So, welcome. Hopefully, I will be able to tell you something interesting about obstacles and how to place them or how to avoid them. Okay. So, this is my first geometry talk in my last 20 years, where there will be less graphs and there will be more curves. So, hopefully, I will do justice to these set of results. So what is the setting of this result is that you're given some environment, right? It could be a graph, it could be some points in R2 or points in RD, and you have some start point and you have a target point. And you have some set of obstacles, like these are my obstacles. And my objective is to remove minimum number of obstacles to reach from start to target, right? So this is the basic setting, and this is a basic set of question that we would be considering in this talk. Now, so for example, if I remove that, then I get a path from start to target, right? So when I say environment, you can think of this as your environment, and you're looking for path inside this blue region. Okay. So now I also have to think region, curves. Okay. Okay. So goal is clear, and what we want to do. So now, it has lots of applications in different settings. So let me tell you one or two applications that at least I am aware of. So this problem came in 2007. It was introduced by Kumar, Lai, and Arora in 2007. And so what was the idea of this? So the setting in which they were looking at is that they have this US-Mexico border, and there are a lot of infiltrators going across. So they wanted to keep some sensors, minimum number of sensors, with the following property that so whenever you go into the sensor, you will be detected. Okay, and they wanted to place few sensors so that at least from your path from Mexico to US, at least at some place you are detected. You don't have to be detected at every sensor, but in your path there is some sensor that is kept that detects you. Okay, so that is the setting in which that was the motivation for them. And they considered this question, right? So now this is where I meant is that it is about placing obstacles. It is not about removing obstacles. So you want to place sensors at places such that any path from S to T, you go and hit at least one obstacles. Okay? So this is what I mean by obstacle placement. Okay? So and they call it this problem is known as barrier resilience. Okay? And the obstacles that they considered is unidisc. So the obstacles that I drew like this, their obstacles were like unidisc because they are like sensors, so they are like unidisc. This problem is still open whether placing these obstacles when your obstacle is unidisc is polytime solvable or algebraic. Okay, so at least till last night, whatever I checked, if someone would have done in last few hours, or if I have missed something on Google search, then I don't know, but the problem is still open. So this is the first open problem. Okay. Now, there's another application that, so my co-author Daniel was talking to one of the people in the group, and they actually said that if you look at this robot motion planning, where this assembly line, you have a static robot which has some few dimensions where it can go, or this thing. So they are like you can think of this as a configuration of robot arm as like some d-dimensional vector, and the movement is like a curve in RD, right? And what is forbidden? What is configuration is like some wall or some container has been placed. So these are like an obstacles that you would like to forbid. And reason for this forbidden is what they call minimum constraint removal. So this problem has also been studied as something called minimum constraint removal, and it was studied by Erickson and Lavely in 2013, a simple but NP-hard motion planning problem. So I'm not very good with applications, so don't ask me any questions about application. All that I read, remembered, mugged, I have told you. Don't ask me anymore. So with that, now let me tell you that these points or these obstacles in R2 or RD, how can you convert that into a graph problem? And that is where my motivation came from, because now I can visualize or think in a way which is a bit easier for me. Okay? So think of this. So now let's forget about RD. Let me just focus on R2 for the talk. Is that think of this, these are like obstacles. These rectangles that you see, they are my obstacles. Okay? And now let me place vertices at each of the intersection points, right? And I should ideally should have put also a vertex which is outside. Okay. Now, how do I draw a graph? Okay. So I'll tell you how do I draw a graph. Is like look at this 1, 2, and this 1. So this tells me that this is an obstacle 1. This will right. And what does this vertex denotes? This is an obstacle 1, 2, because it's an intersection of this obstacle and this obstacle, right? So this is like 2, and similarly you can fill it. Okay, so this is how you can fill these things. Now, what is the meaning of this edges? If you notice that whenever you are moving in an obstacle, right, you will not hit anything unless you go and hit a boundary of some other obstacle, right? So this is why whenever you start from here and you see a boundary that you can hit, I put an edge between them. So that's the way of putting edge. Now, if you notice, this is 1, 2, this is 1, 1, 3. If you think of these obstacles as colors, right, then what are we looking for is the following object. So this is what is called minimum color path problem. So you're given a graph G, color set C, and every vertex is assigned a subset of colors. Okay? So basically it tells you that when I'm in this position, which all obstacles I hit. And what is my goal? And you're given 2 target vertices S and T. My goal task is to find a path that minimizes the number of colors, union of number of colors on that path. So where XP is union of all the colors that is used. Because maybe your path is long, but if the same color is used, you don't care because you're just moving the same obstacle. So once you remove this, this will vanish, right? So my obstacle problem has now moved to this color path problem where you are given a graph, you are given a color subset on each vertices, and you're looking for a path from S to T which minimizes the total number of colors used on this path. Okay? Yes?
So, like about the inverse conversion, so let's say we have a instance of this problem. Like, is there any characterization of when you can convert this into a geometric?
I'll get there, but in general, no.
Okay.
No. So this is way. So like when you say geometry problem, when I say if you look at the obstacles in R2 and RD, you can convert that into this problem. But this is way more difficult and general problem compared to the obstacles problem in R2 and RD. Okay? But there are some special places where you will see that these two problems are same. Okay? So minimum color path versus simple polygons in R2. So look at this input graph G is planar. Okay? Now suppose the input graph G is planar and the color obstacles are connected, which is very natural consideration to make that my obstacles are connected. That means for every C in C, if you look at the vertices that have been assigned this color, it should be a connected set in your graph. Okay? It's connected in G. So now you notice, so if you're talking in R2, you can reduce your problem on a planar graph, right? And there is also a reduction back from this planar graph problem to obstacle problem. So in planar graph, these two problems are same. Okay? But in higher dimension, we cannot talk about the same. Or in general, if you give me an arbitrary instance of min path color problem, I cannot come up with an instance of obstacle problem. Okay? Is that fine? Good. So there is a way. I mean, the reduction is very simple. If you think it's both approximation preserving, parameter preserving, whatever preserving you wish. Okay? So minimum colored path is NP hard. And let me give you a simple reduction from vertex cover. So what is a vertex cover? Your input is graph G, integer K, and the question is there a vertex set S such that if you delete it, graph is independent set, or every edge contains at least one vertex from this set? Okay? It's an NP hard problem, we know. We know that it is even hard to approximate within root 2 minus epsilon, right? And we also know that assuming UGC conjecture, you cannot do better than 2 minus epsilon. Okay? And so here is a simple reduction. So here is my instance. Okay? And I make this diamond graph. What is this diamond graph? So basically for every edge, I have this diamond graph. Okay? So basically, so here is a start vertex, there is a finish vertex. For every edge, you see, I have put AB. So there will be gadgets like this, disjoint gadgets like this for every edge. So next will be AC, AC, next will be AD, this, DD, and C. Okay? Notice that obstacles are not connected in this example. Right? Obstacles are not connected in this graph. Right? This graph is planar, has bandwidth 2, whatever simplest you can think of, this is the graph. So you can start with any graph, make this M edges, and draw these paths. Okay? Now notice, if you have a vertex cover here, what will you do? You go, if you have a vertex cover, just pick up those vertices and you can get a path from here to here. Right? Because everywhere, at least one of them will. So if you come here, I can take this, so you have a path. Similarly, if you do have a path which uses at most k colors, then if you trace back, that will go to give you k size vertex cover in my original graph. Right? Because from every edge, your path will pick at least one thing. Because it's a path from S to T, start to finish. Right? Is it okay? Right? So, but as I said, the problem is obstacles are not connected. But we can just simply add one vertex, give it a color set A, B, C, D, and make it universal to everybody, like B, A, C, all these vertices. Now notice that every color has become connected, right? And the same reduction will hold through. But of course this graph is not planar, right? But it is almost planar, because if you just delete one vertex from this graph, the graph becomes planar. So now obstacles becomes connected, and so even on planar graphs, with connected obstacle, 2 approx is best we can hope for. Right? Why? Because this is a planar graph, because you can take this and connect it without crossing. Right? So this is a planar graph, right? Like it is not as simple graph, but it's still planar graph. Obstacles are connected, and you cannot do anything better than 2 minus epsilon. Okay, so now there are two questions. Can we draw planarity or connectedness? Either of these two. So for general mean color path, it is known that it is NP hard to approximate within any polylog factor by result from 2000. And even if G is planar, obstacles may be disconnected, right? This result is known. And Kumar proved that there is no 1/8 minus epsilon approximate using what is known as dense versus random conjecture. So if you assume this dense versus random conjecture, then actually you can prove even more hardness, like n to the power 1/8 minus epsilon. Okay, so let's see. So whatever reduction we just now saw, let me make it slightly diamond path. So you start and finish. Now imagine that you are given a set family F1, and you have a vertex for each set in this set family. Similarly, you have to select some S2 in some family F2, so on and so forth, right? Then what problem is this? You want to find a set from each of this family so that the union is minimized. Right? So this is a classic problem. And so if you want, this is disconnected, if you want to make connected, just add one such vertex. And so if you drop planarity, immediately you get, this is very hard problem. So immediately get that this is too hard to approximate. So assuming dense versus random conjecture, no n to the power 1 by 4 minus epsilon approximation algorithm for main color path. So the reduction which I just now showed you, that is the best known hardness of approximation for this problem. Okay? Just this simple thing from this union thing. Okay? So even if G is diamond path and obstacles can be disconnected, or G is a diamond path plus one vertex and obstacles are connected, right? We had this result. Okay, so this is the first result that I wanted. So now I'm, yes?
So which problem did you reduce from here?
Oh, this is like you are given some set families and you want to find one set from each family so that the union is minimized.
Does it have a name?
I forgot the name. It's like some, but it is classically well-known hard problem. Okay. So it has a good hardness of approximation. I think union, set union or something it is called. Okay? So now people started to ask, what about exact algorithm when k number of obstacles to remove is small? So there is one naive algorithm that you guess what are the colors on those paths are and drop all other vertices, right? You drop all the colors. Now you are just looking for a shortest path in this. So you can do this in C power k. You can also naively do where n is a number of vertices, because number of colors and number of vertices could be very, very different. So the natural question was whether you have some f of k poly n algorithm. So Ibn Khan showed that it's W1 hard, because just now I showed you the reduction in the previous, the same, that is also a W1 hard problem. So you can use the same reduction to show that this is not possible. Even if G is planar and obstacles can be disconnected, this is not possible. Okay? So, or even if G is planar plus one vertex and obstacles are connected. So, where are we? So, good questions for MCP or multicolored path is the following. General inputs, planar plus connected plus something more. So, this is n to the power 1 by 4 minus epsilon hardness. Best approximation algorithm, right? And here is n to the power half approximation is known by Bandyopadhyay, Kumar, Surya, and Vadrajan. I will outline this approximation algorithm in a minute. Okay? We have 2 minus epsilon hardness, planar better approx than for general case. And what we give in SODA 2021, so it's like 5-6 years old. So we gave a constant factor approximation, and later we found a different characterization which gave a simpler approximation algorithm, simpler parameterized algorithm, but nothing new per se. So it's W1 hard, FPT. So as I showed, Ibn and Lokstanov showed in 2021 that for this case, it is indeed FPT. And what we managed to show by relating it to odd cycle transversal, that you can do as good as this. Okay? So I will get to that result in a minute. Unit disk obstacles, we still don't know whether it is P versus NP. Simple obstacles, by simple obstacle, they mean that if you have axis aligned rectangles with aspect ratio, say some 1 plus epsilon, so like the length and the breadth is like just slightly differ, then the problem is NP hard. So if someone has to use the fact that it is polynomial time on a unit disk, then you have to use some specific property of unit disk. Otherwise, it may not happen. Okay? And there was also, for some simple obstacles of bounded ply, they gave 1 plus epsilon approximation, Corman, Lofer, Sivis, Strauss in 2018. And so does simple obstacles have 1 plus epsilon approximation? Does it have a sub-exponential FPT? I think, yeah, so you do have a 2 to the power little of k hardness for planar plus connected. Can we have a better order 1 approximation? Because we know that it has, the lower bound is 2, but the constants are still very huge. There's a gap between upper bound and the lower bound on the general input. Can we beat this? Yes?
Sorry, well, what happens if you have squares?
Squares?
On the,
Here. I think then you can do it in polynomial time, but I don't remember. Right? Sorry, I'm very, like, this is not my domain to know all the literature on this. But I can check and tell you, okay? I think it's polynomial time when you have unit squares. Okay? So, better order. So these are, like, in my opinion, they are interesting questions that, yes?
So the approximation is always with respect to the number
Of
obstacles. What if you're allowed to shrink, like, or like expand your obstacles a little bit by like some factor? So in
There is-
researching we have this type of approximation as well.
Yeah.
So do people study this here? It seems
Not
relevant
for this problem.
seems
Not for
relevant
this problem.
problem.
Not for this problem. But it makes sense to reduce, because you're right, like wireless sensor, maybe I can reduce the capacity or something. Yeah. But I don't think there is any study of this, at least in this setting. Like shrinking or expansion or something. Yeah. Okay. So here's a 2 root n approximation for general instances, which I find it cute, so at least I thought that I will. So you first guess what is the number of obstacles that you want to remove. So you delete all vertices with at least k colors, right? Because you cannot buy that vertex, because then the union of colors just by this vertex will be at least k. So just forget those vertices. Okay? Buy all colors with at least root n vertices, right? Any color, if it appears on at least root n vertices, take that color as a part of your solution, or or delete those. How many vertices will you delete it? At most, root n such color, right? So you will buy at most k root n such color, correct? Okay. Now, give every vertex weight equal to its color, so like size of its color set. Now, the path on any k color has total weight how much? K root n, because any color only appears on root n, right? So if you look at this path, like this path cannot be more than k times root n, because k is opt, and every color only appears on at most root n vertices. Once you have this, you find ST path P of minimum weight, and you are done, right? So this is at most k root n, and so you output this path P, right? Now, notice, what is the total number of things you used? You bought at most k root n color here, and here is another k root n, so 2k root n, so the approximation factor is. So this is the best known approximation for general input. So I believe there's a lot of scope to improvement, because this sounds too simple that nothing better can be done. So I thought at least I will tell you that you can keep it in your head and you can think where you are going from here. Okay, right? So P had at most k root n colors, and you bought extra k root n color, you're happy. Now, how to place, so there's another question that people have studied is called how to place obstacles or point separation. So here is an environment. And so you are already, you know where to place this. So you know where to place your obstacles, but they are not there. So you have to keep the obstacles on those places such that you kill all the curve from S to T, right? So obstacles have cost, pick a minimum cost set of obstacles so that start can't reach the target, right? So this is the example which I was telling with respect to barrier resilience, right? Okay, so this is what they call point separation problem in this, but I call it placing obstacles to make sure that S to T is not reachable. Okay, so for example, here, if I only place these 3 obstacles, we have force that start cannot reach target. Hardness, again you can reduce from vertex covered, that like you can again reduce from the vertex covered, again you have edges, and what are the colors you are using? Just use the colors on the edges here. So you will get similar kind of hardness even for point separation problem, same as what you had for obstacle removal. Okay, so I will not go into this too deep, but it's basically very simple, very similar. So generally, whatever results happens for obstacle removal, it tend to also apply for point separation. Okay, so same, like literally you can do this. So it's a good task to try it out your own if you want. Okay, so what about planar and connected in polytime? So Cabello and Ganopoulos in 2016 showed that there is a polynomial time algorithm for placing obstacles if you are just trying to do SNT. So, so it was an open problem in from this paper is that what about placing obstacle to separate, say, 10 points from each other? So it's like a multi-way version of this. So you have some 10 points and you want to separate it. And okay, so this is the starting point for some of our results was. So now I will tell you what we do. So to do that, let me take a detour. You all have seen separators in planar graphs. So how does a separators in planar graph looks like? So you saw interesting things. So this is a separator. So basically, a separators are nothing but you can find a region that keeps S in one side, T in the other side. Okay? Which basically means that this is basically a radial cycle. But what is a radial cycle? So let me tell you what radial cycles are. So you take your planar graph, add vertex to face, and just add this, make this vertex adjacent to every vertex on this face. So these are called radial graph, or this is also called vertex face incidence graph. So one side of bipartite graph you have a vertices, other side you have faces, and if this vertex appears on this face, then you add that. So this cycle that you are looking for, this radial cycle, is basically a radial cycle in this vertex face graph. Okay? Which separates your region into two pieces, one containing S, other containing T. Right? Such that, look at this curve from S to T, right? It should intersect it. But how many times? Right? So in fact, you can generalize these results not to cycle, but closed radial walk. And the idea and separators in planar graph is, fact is, let Q be any ST curve. A vertex set is an ST separator if and only if there exists a closed radial walk in G that only uses vertices in S and crosses Q odd number of times. So try to do S and T right into plane and try to draw a cycle around this or a walk around this which only crosses this curve even number of times. You will never be able to separate S from T. Okay, so it's a nice, if you look at the proof, you need all this Jordan curve theorem and all, but this is the basic fact that you can use. And this is the result which we will use to prove our results. Okay, so how do we construct an obstacle graph H? So here is my, right? So imagine that these are my obstacles. So what is obstacles? So obstacles are this, so I have taken planar graph. So what is my obstacle? This is like some connected set, right? So there's a red region, there's a green region, there's a black region, and there's a blue region. So colors of G corresponds to vertices of H, right? And for every colored class or every connected set, I just choose a reference point. So I arbitrarily just choose a reference point. Yes?
So the planar graph is embedded?
It's embedded.
Okay.
Okay? You can start with any embedding, but just fix one embedding for your. So now I fix a reference point. Okay? And now, what are the edges? So edges are radial walk between reference vertices. So for example, look at this, right? So this is an outer face, right? So every vertex that is an outer face is connected to some vertex which is outside on this. So I can go to blue vertex from red vertex by this. So I put an edge between them. Okay? So this is how I put edge between all of these. Now what I do is that I fix one curve, one S to T curve, fix one S to T curve, any arbitrary S to T curve, you fix, right? And now you will start to give parities to each of these edges that I'm going to put. So how do I put parities to edges? So we are going to label edges by number of times they cross my reference curve Q, right? So if you look at two reference vertices, if there exists a curve which goes from this vertex to this, and crosses this odd number of times, I'm going to call it an odd parity. If there exists a curve which crosses this curve even number of times, then I give a even parity or 0 or 1. Okay? So for example, look at this blue and the green vertex, right? So if you look at this, this does not crosses this, right? So I just added one edge. But if I look at this, another blue to green path that crosses this cut once. So now I will give another edge with a different color. So think of this, if it crosses odd number of times, it is 1. If it is crossing even number of times, it is 0. Okay? So this is how you can define your obstacle graph, okay, with parity. Now what we are able to show, like more thing. Okay. So what is a color separator? A color separator is a set S of colors, and that every ST path P satisfies the colors of P intersection S is non-empty. And so the edges, shortest path, the way edges occurs in the minimum color path, colors occurs. Cuts goes to color separators. And what we were able to show, lemma, let S be a set of colors, then S is a color separator if and only if you look at the graph induced on S contains an odd label cycle. Right? So what we are able to show that if S is a set of colors, right? Look at the obstacle graph on those set of this, that should contain an odd label cycle. Okay? So this is a characterization which allows you to nicely go through everything. This direction is easy. This direction is slightly harder, but not more than a page proof. And now, let me say, because of that, what it implies. So what is the magic of H? So problem, you want to place obstacles. That is minimum cost color separator. It is minimum cost odd label cycle in H. Right? So this gives you another simple polytime algorithm of Cabello and Ganopoulos. Minimum color path is minimum set S so that C minus S is not a color separator, which is same as minimum S so that H minus S has no odd label cycles. Right? So they just translates, once you have this result, it translates into these things. So I will leave this for something else. So now obstacle removal via odd cycle transversal. What is odd cycle transversal? You are given a graph G, integer k, and you want to delete as few vertices as possible so that the graph has no odd cycle or it is bipolar. So it is also NP hard, has square root log n approximation, and it has this kind of algorithm. Okay. Now, how do you relate obstacle removal to odd cycle transversal? So think of this, your labeled graph. You just subdivide every 0 label, right? Now every odd label thing has become odd cycle because 0 has become even. That's it. So now you can directly apply all these algorithms. You don't have to do this 50-page of sausage paper and do all the geometry once you have this. So this is done. More magic from H. So they wanted to place k obstacle to separate k points from each other. Polytime algorithm for fixed k, yes. So for every pair Vi, Vj, we can a graph, I'll make this Hij, the obstacle graph on vertex at C. And you can show that S subset of C separates Vi and Vj if and only if there exists odd cycle or odd labels in this. Now all Hi have the same vertex at C because they are same set of obstacles. S subset of C is the solution if for every Ij there exists odd cycle in this graph. Now it's all about getting this S, and what we show is that basically the union of this order k square cycle has order k vertices of degree at least 2. So you guess this and you try to find the parity things around this, and then you get this kind of algorithm. Compute shortest path of given parity between them. Okay, so what did you just see? So I'm almost done. 1 more minute and I should be done. So we have seen hardness for min color path on general instance. I did not tell you order 1 approximation, but at least I told you square root log n approximation because you just approximate odd cycle transversal for which there is square root log n, right? But you can salvage more because of the instance and show that there's a constant ductility gap between LPs, but then you have to mess with LP to do these things. Okay? Hardness of approximation for placing obstacles on general instances, a polynomial time algorithm for placing obstacles in planar color connected instances, even to disconnect k points for fixed constant k. But before I tell, I have to tell something that recently it has been brought to us. Okay. And I think it will also say something which was told in the first talk. So I think it's important that we go back. God, how bad I am. We're almost there. Okay, something to important point. So this result of our uses this result of Lee about the string graphs and everything, which seems to have some flaw. So we build on their result. So it seems to have some flaw. I think there's some provably flaw. So he proves this result in much more generality than just string graphs. But we need only for the special case of string graphs and this. Someone, at least now we have been told that coming up with a different proof, at least for the string graph, that will work, and he's going to put this in archive soon. So hopefully all these results will survive, because we do use the result of Lee during our rounding. So this is important to point out. Otherwise, I mean, we shouldn't be building on something. So it has been brought to our attention. So I thought it's important that I point it out to people. Okay. So thank you. That's all that I wanted to tell. Thanks a lot.
You can take one question.
Thank you for the talk. You use the conjecture, it was called, I don't quite remember, dense versus
random.
What is this conjecture?
So it is some with respect to some planted click and this. Yeah, so I just don't ask me for this.
Okay, fair.
Like 5 years old, so it's not that I have it. But it is about with respect to some planted click in some random instances.
Okay, thank you.
I can look back and tell you. Yes?
In this framework thing, you are using these radial graphs.
Right.
These you can also define in bounded genus graph. So do these work there?
Radial graphs are still planar graphs. So I can use much more simpler properties than defining genus and this thing. Right? Because look at this, your graph, right? You're just putting a vertex inside each face and making it adjacent to this. This is still a planar graph, because we have given an embedding already.
So given an embedding on a torus, say, then can you do it?
I think you should be able to do it. Like up to genus, you can define this notion of radial graphs, but I do not think beyond that you can define these things.
Yeah, we can take further questions during the lunch break in the interest of time.
Yes.
Thank Professor Saket once again. So our next speaker is Professor Akanksha Agarwal, a Veena and Indu Prakash Keri Faculty Fellow at IIT Madras. She completed her Masters here at IISc, PhD at University of Bergen, and held postdoc positions at Ben Gurion University and the Hungarian Academy of Sciences. Her research interests span parameterized complexity, graph algorithms, computational geometry, and fine-grained complexity. In today's talk, she will discuss applications of constraint CSP to parameterized geometric algorithms. So please join me in welcoming Professor Akanksha.
Thank you for the warm introduction, and thanks to the organizer particularly for inviting me here. So I'll be speaking about constraints, how structured CSPs and its algorithms can be used in obtaining parameterized algorithms for geometric problems. So since we had constraint satisfaction problem in the title itself, let us begin by understanding that. A typical instance of constraint satisfaction problem has a bunch of variables, a finite set of variables, say x1, x2 up to xn, and each variable comes with a domain. This domain could be finite or infinite in its full generality. So we have domain di associated with the variable xi, and we have a bunch of constraints. Finitely many constraints. Here we have m constraint. So what do we mean by a constraint is? So each constraint is a pair where the first first element of this pair is a tuple of variables. For instance, if x, y, z are my variables, then the first element for this constraint C1 is this tuple x, y, z. And then we have a set of allowed values for these tuples. In this example, for the tuple x, y, z, as a tuple, they can get values 1, 2, 3, 5, 2, 6, 2, 1, 1. This set of allowed values can either be given explicitly or implicitly. Okay? So for instance, you can state that x plus 5y should be equal to 0, in which case you are encoding both the tuple of variables that you have and the kind of values they can get together. So, and the question is, can we assign each variable a value from its domain so that we end up satisfying each of the constraints? Okay? So this problem, as you may guess, it's really, really hard. In fact, when parameterized by the number of variables, we don't even expect an algorithm whose running time is f of n for any function, any computable function f, poly in the input size. And this result holds also when each constraint involves at most 2 variables. Okay, so it's among really hard problems. So we will restrict ourselves to a special structured variant of the problem, which we call as monotone 2 CSP. Here we have, again we have a bunch of variables, a finite set of variables, and now the domains are finite, okay? So for each variable, we explicitly have an input domain di, which is a finite set, and we have a structured set of constraints. So let us understand how our constraints look like. So each constraint firstly involves at most 2 variables, and the constraints are of the following form. So suppose x and y are variables, so a constraint can be x greater than equal to f of y or x less than equal to f of y, where this function f is either a non-decreasing function or a non-increasing function. So this is why the word monotone in the title of the problem. Okay? And again, the goal is to check if we can assign values to each of the variables from their domains so that all constraints are satisfied. Okay? So this problem is polynomial time solvable using, so you can reduce it to an instance of 2SAT, and that's how you can get an easy polynomial time algorithm for this problem. We will not look at the algorithm itself, but trust me that we can do this. Okay? So we'll assume that we have a polynomial time algorithm for this problem, and using this we'll obtain, we'll see at least one application of how we can use this algorithm to obtain parameterized algorithm for some geometric problem. Okay? So we have found a bunch of application. I'll be focusing on the art gallery problem. So let us begin by understanding what this problem is. So I'll build up some notation. I think it's a geometric crowd, so most of you might be aware, but just for completeness, I'll say it anyway very briefly. So suppose you have a polygon. It's a simple polygon. It does not has holes. It is not self-intersecting. So if you have 2 points S and T in this polygon, we say that they see each other if the line segment between them is completely contained in the polygon. For instance, in this picture, if you look at the points S and T, the line segment between them is fully contained in the polygon, so they see each other. Whereas if you look at these points S and Q, they do not see each other. Okay? And so for a vertex in the polygon, it's a corner point, using which you specify the polygon. Okay? The points using which you specify the polygon is what I call as vertices of the polygon. And I say that a vertex is a reflex vertex of the polygon if the interior angle at this vertex is strictly more than 180 degrees, and otherwise it's a convex vertex. Okay, so in the art gallery problem, as an input we are given a simple polygon and an integer k, and the question is, can we place at most k guards in this polygon so that we end up seeing the whole of the polygon. Okay? So for instance, if k is equal to 2, in this example, if we place 2 guards here and here, together they see all the points in the polygon, so it will be a yes instance. So there are various variants of the art gallery problem that has been considered in the literature. They are all quite well studied based on where we can place the guard and what all points of the polygon we are required to guard. So based on these two constraints, we get different versions. Some of the variants can be defined as follows, where suppose X is the set where the guards can be placed, and Y is the set of points from the polygon that needs to be guarded. X could be, say, vertex set of the polygon, or the boundary of the polygon, or all the points in the polygon. Similarly, Y can be one of these three things. Based on the choices of X and Y, you get something that we call as XY art gallery problem. And we will be focusing on the vertex version. So, and the most classical formulation is when X and Y are all the points of the polygon. So, some brief history. This is not a thorough literature survey, but a very, very brief history. So, the problem was posed back in 1973, where the question was asked that how many guards are always sufficient to guard a given polygon, a simple polygon, where n is the number of vertices of the polygon. And it was shown that n by 3 guards are always sufficient and sometimes necessary. We have NP hardness results starting from an NP hardness that needed some holes in the polygon, and then those constraints were lifted. And most of the versions, so the versions that I described, this XY version, where X and Y are either the vertices, points, or boundary for any choice of the pair of them, they all are known to be NP hard. And for exact algorithm, a solution using n by 3 guards can be computed in linear time. And for this point one, the classical formulation of art gallery that has an exact algorithm whose running time looks something like this. And it uses some heavy machinery where you turn the instance to solving some polynomial inequalities, and that's how you get this algorithm. So in parameterized complexity, so the problem is quite hard. So if you want to come up with an algorithm whose running time is f of k, k is the number of guards that you want to place into polynomial in the number of vertices, such an algorithm is not possible by a result of Bonnet and Milza. And thus a natural next question is, can we parameterize by the number of reflex vertices? And let us understand why reflex vertices all of a sudden. So given any polygon, so suppose if the polygon has no reflex vertex, then one guard is always sufficient, so that's a trivial case. So let's get it out of the picture. So the more complicated case is when the input polygon has a bunch of reflex vertices, but in this case we can always show if you place one guard at each of the reflex vertices, they together can guard the whole of the polygon. So parameterized by the number of guards alone, we don't have an FPT algorithm, which is an algorithm whose running time is f of k into poly in n. So now then the number of reflex vertices is a natural upper bound for the number of guards we need. So k, we can always assume that k is at most r, because otherwise we can trivially say yes. So this is the next natural parameter, and we consider this, and we show that actually we can obtain an FPT algorithm, which is an algorithm where the running time is f of r into poly in n. R is the number of reflex vertices, and this is the brief sketch of how we obtain our algorithm. And this is also a sketch of how we can obtain algorithm when we want to use some structured CSPs. So what we do is, whatever your problem of interest is, you guess some structure about the solution. So you guess enough structure so that now with more information on how the solution looks like, you can encode this as an instance of CSP. Okay, so I'll explain it briefly using the example of art gallery, the vertex version, where our goal is to place guards only on the vertices, some of the vertices, minimum size set, minimum such guard set, and our goal is only to guard the vertices of the polygon. Okay, so we'll be working with that variant, and what we'll do is we'll start with the instance of the problem, guess the structure of the solution, and get a bunch of structured instances where we know how solution looks like, And once we know that, so we guess enough information so that it is encodable as some special CSP, and the special CSP for us will be the monotone 2 CSP that we have seen. Okay, so we will prove this result. So this is a result with these people. Sakit is here. So let us begin. So I'll introduce some notations. So what we'll do is, we have this given polygon. We will fix we'll label one vertex as 1, and walking from 1 towards the end of the polygon, we'll keep labeling the vertices like 1, 2, 3 and so on up to n. Okay? So this will help us like encode our functions as some monotone function. So this is why we fix this cyclic labeling of the vertices of the given polygon. What we'll do is, we will now define convex regions of this polygon, which is nothing but look at the vertices that are sandwiched between two consecutive reflex vertices in your polygon in the cyclic order. That is what we call as a convex region. For instance, if you look at this vertices 2, 3 and 4, it forms a convex region by our definition, because between them there is no reflex vertex. If you go further left, you get a reflex vertex. If you go further on the top or the next vertex, you get a reflex vertex. Okay, so in this polygon, we have 3 convex regions. So now let's try to gather structural insights to turn it into structured versions. So first let us understand what all information we will guess. Okay, and then we'll see how with these amount of structure we can actually just write it as an yes.
Can you please go back to the last?
Yeah.
So convex region won't essentially mean that everything in the particular convex sub-polygon will also be inside the simple polygon, right?
Yeah, we are only looking at vertex sequence. Okay? Yeah, yes, exactly. Yeah, it's a sequence of vertices. So yeah, we are more in the discrete setting.
So division must not be contained in the simple polygon. The region enclosed by the convex chain must not be contained in the simple polygon. Or it doesn't have to be.
Yeah, exactly.
Yes, it doesn't have to.
Yeah. So it's just that if you include one more vertex from this is the start vertex, the lower vertex. If you include one more vertex to the left, you end up getting a reflex vertex. Similarly on the other side, it's a maximal sequence of convex vertices. Okay. Okay. So let's understand the structured version of the art gallery that we'll be working with. So what we'll do is, so we have a bunch of these convex region and reflex vertices. By this set fancy C, I will denote the union of the set of convex region and the reflex vertices. Okay, that is what this fancy C is. So the first function that I will have is the number of guards placed in each of the convex regions and reflex vertices, if at all we place guards on the reflex vertices. So this function hash GP gives us the number of guards placed in the convex region or reflex vertex. Of course, when it is a reflex vertex, it should be either 0 or 1, but anyway, it doesn't matter. So suppose here hash GPCI is 0. For this convex region, we'll not be allowed to place any guard. Here hash GPCA is 3, so we will be placing 3 guards, and so on. Then we will have a function hash GS, which will tell us how many guards are required to see a convex region or a reflex vertex. For instance, here you have this convex region Ci, where hash GS of Ci is 4. Then 4 guards together will be responsible to see all the vertices of this convex region. This is what this function hash GS tells us. Okay? Then we will also have, for every element in this fancy Ci, we will have a function that tells us how this convex region is seen in the following sense. Okay? So, suppose that for this convex region Ci, we need 4 guards, which is given by the function hash GSCI. So 4 guards are responsible to see this convex region together. Then this how Ci will tell us, look at the first guard who is responsible to see this convex region. where does this guard come from and which is the guard number. So suppose we have, so okay, firstly this hash GSCI is 4, then it will be the convex region CI. When we look at the how it is guarded, it will be divided into 4 consecutive regions, and together it covers the whole of the convex region. And suppose how CI1 is CA comma 2. Okay, so look at the first piece of how this convex region CI is seen. If this function tells us this it's a pair CA comma 2, then the second guard placed in the convex region CA will be responsible to see the first piece of this convex region CI. Okay. Similarly, so the guard that we placed, the second guard that we placed in the convex region CA must see the first piece. Similarly, if how CI2 is U comma 1, then the reflex vertex U should see some vertices. And similarly, if how CI3, the third guard responsible to see this convex region, is some CA comma 3, then the third guard placed in CA will be responsible to guard the next piece till we reach the end, in which case the last guard also must see the last vertex. Okay, so these are the functions that we will additionally have that tells us the structure about the solution, how the polygon is guarded. Okay, so the point is, if you want to go from the vertex version of the art gallery to the structured version of the art gallery that we saw, all you need to do is guess or iterate over each choice of these functions, right? So notice that we have already argued the number of guards needed is at most the number of reflex vertices, right? So here this number k is at most r. So if we guess these functions, we can obtain a Turing reduction from the vertex version to the structured version, where the number of instances we create is something like r to the order r square. Okay? So recall we have this function how Ci for each element in Ci from the fancy set C. This is why it becomes r to the order r square. Yes?
Sorry, so GS guesses which CI sees CJ?
You just a moment. So you mean GS?
Yeah.
It tells you how many guards are required to see the convex region or a reflex vertex. Okay? For instance, if you have hash GSCI equals to 4, then 4 guards will be responsible to together see this convex region CI.
And we can further guess where they come from.
Exactly. That's what is given by this function how CI. Okay? So where is the first guard that is required to see this convex region coming from? So for instance here how Ci comma 3 is Ca comma b, then the third guard placed in Ca must be responsible to see the third piece. Okay? Yes?
Where is the convexity being used?
So, okay, I'll come to it. Okay, it is used, so when we try to encode it as monotone 2 CSP, there will be used. Okay? So as of now we are not using, because these functions we can guess anyway, right? So till now we have not used it. Okay, so this is how we can turn the art gallery instance into structured version of the problem. And now we'll see how we can solve each of these structured instances using an algorithm for the special 2 CSP, which in our case is monotone 2 CSP. Okay, so let's see how we can solve the structured version using monotone 2 CSP. So just a few functions that will be useful. So suppose you have this convex region Ci and a convex region Cj. This also extends for when Ci, one of Ci or Cj or both of them are reflex vertices, but the most general thing is when they are convex regions, so I'll state for them. So for a point P or a vertex P in my convex region Ci, I define the function first PCj, which is what intuition would suggest. Look at the lowest or the first vertex that P sees in this convex region Cj. Okay? So first of P comma Cj is 12 because P does not see 10, it does not see 11, but it sees 12. Right? So it is the lowest vertex that P sees in the convex region Cj. Okay? And analogously, you can define the last seen vertex, where you will look at the last seen vertex. If a point does not see any vertex, we'll assign it null. Okay? So one of the useful properties, and here is where we crucially need convexity, is that if you look at any point P in Ci, then it sees all the points that appear between the first and last vertex. Okay? So this is completely seen. Okay, either it sees nothing or it sees like everything continuously. And this will help us encode the instance as an instance of monotone to CSP, so that the functions are monotone. Okay. So now, so the point is just intuitively why it is. So intuitively, these functions first and last, why are they monotone? Okay, let's try to understand that. Just an intuition. So suppose we have this convex region Ci and Cj. Let's start walking from in the convex region Ci from the lowest vertex to the highest vertex. Okay, and let's see how the vertices. What is the first seen vertex? Okay, 5 does not see anything, so we have a nil. Then 6 for first of 6 comma Cj is 11. First of 7 comma Cj is 12, and so on. So the point is, due to these reflex vertices, if you are going from left to right, the function either stays at the same place or it is increasing. Okay, either it's increasing or it's decreasing based on the labeling. So this is why intuitively we get monotone functions. So these function first and last that we have defined, this is the intuition why those are monotone functions. Okay, so you walk from left to right, then the function, these functions are actually either non-decreasing or non-increasing. And so now let's see how we can encode instance of structured art gallery as an instance of monotone to CSP quickly. So for every C in fancy C, suppose, so recall hash GP tells you the number of guards that we need to place in C. So for every such guard we create a variable. So this is our variable set. And then what we want is, so suppose how Ci1 is Ca comma 2, then the second, whatever value you assign to the variable x Ca comma 2 must, so look at the first of that vertex, right? In the convex region Ci, it must see the first vertex. So we have a constraint of that form. Then that guard sees a piece of some region starting from the first vertex till certain vertex. Now let us look at the next guard that is responsible to see. It must start seeing vertices on or before the next vertex from the previous ending, the previous vertex that was last seen. So this is why we want that the first of this guard, whatever value you assign in the convex region Ci, must be less than equal to the last seen vertex by the previous guard plus 1. Plus 1 because if 7 was already seen, you can start seeing from 8. Okay? And you keep adding constraints in this form. And additionally, you want that the last vertex must be seen by the last guard responsible to see this convex region. And I have at least shared the intuition why these functions first and last are monotone. So thus you can argue that these are in fact monotone functions formally, and now all it boils down to is solving monotone to CSP, and this gives us the algorithm. So here I will quickly end with these open questions. Our approach extends for also boundary vertex and vertex boundary version, where x and at least if one of x and y are vertex set and the other is the boundary one, then our algorithm will work by appropriate discretization. But what about the other variants, right? So that is still open. Some of these are also, there exist hard. And can we use similar approaches? So here our instance of monotone, the version that we defined of CSP was solvable in polynomial time. Maybe you can also work with a harder, slightly harder version of the problem, which has some f of n into poly in the input size time algorithm, where n is the number of variables. Still this approach will work. So can we follow this prototype and obtain more algorithms? And yeah, I'll end here. Thank you. it's r to the order r square, because otherwise I into poly n. Because we have, what we do is we create these many instances of the structured version, and each of them is poly time solvable.
Any lower bounds on?
We don't know.
Hello?
I mean, yes.
Algebraic theorem wants to cover the entire internal region,
The point version, yes.
but any version. Because if you can put reflex vertex
Yes.
guard, you can see the entire boundary, but you may not see the entire region.
Yes, that is true. So this is why we had defined this version. So all these variants are NP hard, where, so choose your x and y, where x is either the vertex at boundary or the points, and y is either the vertex at boundary or the point. For all choices of x and y, the problem is still NP hard.
No, question is placing guards
Yes.
at reflex vertex may not see the entire polygonal region. It can see only the
No,
boundary.
so we were working with the vertex version, right? So it
Anyway, even in vertex vertexation, it can be constructed that some portion in the internal region are not visible.
no, internal, but we are not concerned, right? We are only.
Oh, you are bounded.
Yes, vertex version.
But you can also have a polygon
Yes.
where all of them are reflex vertex and except one vertex is convex.
So
Your whole chain and one vertex, and that vertex in the convex vertex can see the entire polygon.
yes.
So your convex regions are all segments and reflex ones.
Yes,
How
but
do you
what?
handle that?
Yes, what we are saying is that the number of, so apart from the trivial case where we have no reflex vertex, where one guard is sufficient, in every other case, k can be upper bounded by the number of reflex vertices.
Oh,
right?
that's
All
true,
we
but
are
here
using
you
is
have
this.
only one vertex, convex vertex where guard is enough,
Yes.
and entire thing is a reflex chain.
Yes,
So
because notice that we are guessing these functions, right? So notice that I'm, just a minute. So here I can have that I place guard in exactly one convex region. So look at the convex region, which is a line segment for you. So the guess where I have hash GP of that convex region as 1, and for everything else it is 0, this will exactly be dealing with what
no, it will not.
No, it will.
No.
No, it is.
No, we
I mean, we can argue about it, but it will.
We can argue for
Sure.
hours, but we will.
No, because it works. The algorithm is
Later, we will
Sure.
talk about later.
Okay, any more questions? If not, let's can the speaker once again.